Hello and welcome to this webinar. My name is David Thomas. I'm a software engineer at Amazon Web Services working on our deep learning team. I work on Amazon Elastic Inference. In this presentation, you will hear about how you can lower your deep learning inference costs for your PyTorch models using Elastic Inference. First, I'll give an introduction to some of the problems you run into running inference applications, what Amazon Elastic Inference is, and how it helps you solve those problems. Next, we'll give a demo of how to use Elastic Inference with PyTorch and Amazon SageMaker. We'll follow that up with a demo of using Elastic Inference with PyTorch on EC2 instances, and then we'll open it up for Q&A. First, let's start with the problem we're trying to solve. The costs associated with running applications that use deep learning fall into these two main categories: training models and making predictions with them, also known as inference. We're constantly working towards training models faster and more cheaply by offering faster processors and GPUs and better algorithms for various use cases like computer vision, natural language processing, and many more. We're also always working on improving GPU utilization to reduce training times. But training is typically a small part of your cost for deep learning. Once your model is trained, say on a fleet of P3 GPU instances, making use of the model typically requires running many inferences as part of applications that run 24/7. So in our experience, inference is actually a larger part of your deep learning infrastructure expense than training, with estimates of up to 90% of your deep learning costs. Let's look closer at the problem of right sizing. We see a number of inefficiencies in the available infrastructure that makes up over 90% of the costs of deep learning. First, using GPUs for inference greatly improves the inference latency compared to using CPU instances, which is great for users of your application. But standalone GPU instances are expensive and are typically purpose-built to train models quickly and efficiently, but they're oversized for inference, as inference happens to be a very different kind of workload than training. While training jobs batch process hundreds of data samples in parallel on the GPU, most inference happens on a single input in real time. And that consumes only a small amount of the available GPU computational capacity. Even at peak load, we very rarely see full GPU utilization when running inference. This is wasteful and costly. Secondly, different models need different amounts of GPU, CPU, and memory resources. Selecting a GPU instance type that's big enough to satisfy the requirements of the most demanding resource often results in underutilization of the other resources, and therefore high costs. What if you could keep your application on your familiar CPU instance and attach just the right amount of hardware acceleration for inference? That's where Amazon Elastic Inference comes in. Amazon Elastic Inference, or EI, helps to lower the cost of running deep learning applications by giving you the amount of GPU acceleration that's right-sized for your inference application. EI helps you size the CPU, memory, and GPU acceleration requirements of your application independently. So for your computer vision, NLP, and other applications, where you need smaller amounts of CPU and memory compared to GPU acceleration, you can now choose a smaller CPU instance and attach a GPU-powered EI accelerator, choosing from a range of sizes that provides you the latency your application requires, while helping you fully utilize its capacity and lower your costs. You can attach EI accelerators to EC2 instances, to ECS tasks, and SageMaker to apply acceleration flexibly without additional infrastructure management. When you use EI with SageMaker in particular, you can lower your costs and also have a fully managed experience. Whether you are using dedicated instances for inference or co-locating the rest of your application stack with the inference, EI can help you save costs with either model. SageMaker fully manages the inference experience for you. You can prototype your deployments with SageMaker notebooks. You can then deploy models on SageMaker endpoints with cost-effective EI acceleration instead of using standalone GPU instances. SageMaker hosting will automatically manage the instance fleet size for you, including the EI accelerators, depending on your usage. If you're using EC2, you can use EC2 launch templates to configure EI accelerators for your instance. That allows you to scale your instances along with their attached accelerators as a single unit with EC2 autoscaling. So when you use autoscaling groups in EC2, you can control your desired capacity for instances and their accelerators for your application's varying needs. EI accelerators are available today in multiple sizes, each with different amounts of single precision FP32 and mixed precision FP16 compute capacity, as well as different amounts of available accelerator memory. You can use as low as 2 GB of accelerator memory to as high as 8 GB of accelerator memory. These are available at prices that are significantly cheaper than GPU instances. The smallest accelerator costs just 12 cents an hour in US regions. EI is available in 6 different regions worldwide. Note that we have 2 EI accelerator families, EIA1 and EIA2. Our latest family of accelerators is EIA2, with twice the GPU memory of EIA1 at a lower price per hour than EIA1. Moving forward, we'll also extend EIA2 to other regions as well. So how should you choose an accelerator type? Demands on CPU compute resources, RAM, GPU-based acceleration, and GPU memory all vary significantly between different types of deep learning models. The latency and throughput requirements of the application also factor into which instance type and the amount of EI acceleration that you need. Consider the following when you choose an instance and accelerator type combination for your model. First, determine the target latency and throughput needs for your overall application stack, as well as any other constraints you may have. For example, if your application needs to respond within 200 milliseconds, say, and data retrieval, including authentication and pre-processing, takes 110 milliseconds, then you have a 90 millisecond window to work with for the inference request itself. So using this analysis, you can determine the lowest cost infrastructure combination that meets these targets. Also keep in mind that different models need different amounts of GPU memory available at runtime. Pick an accelerator size accordingly. So start with a reasonably small combination of resources. For instance, maybe start with a C5.x large instance type along with an EIA2.medium accelerator type, which has up to 1 teraflop of FP32 performance and 2 GB of GPU memory. You can then size up the instance or the accelerator type independently, depending on your latency targets and tests. Some use cases might require memory optimized instances, either R or M, for the application needs. If you load multiple models to your accelerator or the same model from multiple processes, you may need a larger accelerator size for both the compute and memory needs on the accelerator. Since Amazon EI accelerators are attached over the network, input-output data transfer between instance and accelerator adds to the inferencing latency. Using a larger size for the instance or the accelerator may reduce the data transfer time and therefore reduce overall inference latency. Finally, you can convert your model to mixed precision, which utilizes the higher FP16 throughput capability of EI for a given size to provide lower latency and higher performance. So to summarize, know the GPU memory requirement, your target latency, and your application requirements for your client instance. You can then do a proof of concept to see if your latency requirements are met. And if not, you can size up the accelerator, the instance, or both. Let's talk about the frameworks we support. EI supports PyTorch, TensorFlow, Apache MXNet, and Onyx models. The service provides EI-enabled software packages for each of these options that let you deploy models on these frameworks with little to no code changes, as you'll see. The EI experience is very similar to using a GPU in your code. These packages automatically discover the presence of an accelerator and efficiently offload operations within your model to run on the attached accelerator. If you're using SageMaker, these packages are provided out of the box. You can find them within our deep learning AMIs for your EC2 instances and in deep learning containers. You can also download the appropriate pip packages via S3 to install on your instances in your custom environment. Now, let's talk about PyTorch, the latest framework to launch on EI. PyTorch is a deep learning framework Popular with developers and researchers alike, it's known for its imperative programming model, which many people find easier to learn than the static graph-based approach traditionally used in frameworks like TensorFlow. This means when you execute a line of PyTorch code that looks like a tensor operation, say, that operation runs right then. Another way to put it is that your code is the model. This way of doing things is easier for prototyping and debugging, allows you to write code that looks very close to what you'd write using a library like NumPy, but with extra features like support for GPU acceleration and for automatically computing the gradients needed to train deep learning models. On the other hand, though, for high-performance production inference, the static graph-based approach is actually helpful for a few different reasons. Static model graphs allow for a Python code-free declarative description of the model. This allows the model to be processed, optimized, and run apart from the Python environment used to develop the model in the first place. So PyTorch, starting with version 1.0, introduced TorchScript to provide the best of both worlds. So what is TorchScript? TorchScript is a way to create serializable and optimizable models from PyTorch code. First, you develop your model as a standard PyTorch module, and then convert it to TorchScript using one of the provided methods, tracing and scripting. Both are easy to do, but differ in how they work. So let's talk about tracing. Tracing runs your PyTorch model on an example input, and then records the operations that happen. Then it saves that as a TorchScript model that performs that sequence of operations. So scripting is different. PyTorch provides a script compiler which analyzes your Python code and translates it into a TorchScript graph representation. Unlike tracing, it analyzes the code directly rather than running it. Scripting may require adding some type annotations to your Python code to help out the compiler, but the upside is that it preserves control flow, and I'll explain what that means. You don't have to provide an example input, and the produced code is as flexible as the original Python code. For example, if your model is intended to do one thing with small inputs and another thing with large inputs, and you trace it with a small input, the recorded sequence of operations that tracing records will only include the code path for small inputs, since that's the input you gave it. Scripting doesn't have this problem as it analyzes the code directly. Both the small input and large input code paths would be preserved. This is relevant for Elastic Inference because EI support for PyTorch is built on top of TorchScript. Note that due to how EI currently handles control flow, your model will most likely get the best performance with EI if you are able to use tracing. So now let's jump into a demo of using Elastic Inference for your PyTorch models using Amazon SageMaker. Amazon SageMaker has Elastic Inference support right out of the box. By specifying an EI accelerator type when deploying your endpoint, you can launch a SageMaker hosted endpoint with an attached accelerator. So to set things up, what I've done here is I've launched an EC2 instance with deep learning AMI with an IAM role allowing SageMaker access. And then I launched Jupyter Notebook on that instance. So Jupyter Notebook is what we're looking at now. It's important when you're using PyTorch with Elastic Inference to ensure you're using a compatible version of PyTorch. EI currently supports PyTorch version 1.3.1, so keep that in mind. By the way, if you're wondering why I'm not using SageMaker Notebook instance, that's exactly why. There currently, at the time of this demo, is not an EI-compatible SageMaker Notebook environment, but it's in the works and it's coming soon. And for demo purposes, I'm using a pre-run notebook, so all the outputs are here and we can look at it in its entirety. So let's walk through it. First, you can see that we're using a DenseNet 121 model from TorchVision with pre-trained weights. So this model's already been trained. This is a standard PyTorch module. It's not TorchScript yet. And if we used our own model that we had trained, nothing after this point should change. It would work the same way. So once you have your model, we toggle inference mode by calling eval. And now is when TorchScript comes into the picture. We get a random input of the right size. And then we pass that to torch.jit.trace. This traces the model on this input and turns it into a TorchScript model. And we can actually look at the graph that it produced. So you can see it produces this graph representation. The details don't really matter there, but that's just showing that it produces a graph. So once we have a TorchScript model, we save it using torch.jit.save to save it to a file. And after that, because we're using SageMaker, we package it into a tarball so we can upload it and use it to host an endpoint. The next thing we do is we upload that model data to S3 using the SageMaker SDK in just a couple of lines here. SageMaker requires what's called an entry point script, but we're okay with all of the default behavior, so we just have to create an empty file here. That's what this is, called script.py. But then we're ready to create the endpoint to actually host the model. We set up some configuration parameters for the hosted endpoint, including the region and the SageMaker role, as well as the endpoint name. But notice in particular the instance type of ml.c5.large and the accelerator type, ml.eia2.medium. This is where we tell SageMaker we want to use an EI accelerator with our hosted endpoint and choose the type, in this case, eia2.medium. Next, we create a PyTorch model, telling SageMaker how to find our model and which version of the framework we want to use. It's important here to pick an EI compatible version. You can see we've picked 1.3.1. Next, we call deploy on this model, specifying the configuration parameters we specified before. We're running with an instance count of 1, but you could use a larger fleet if you needed it for your application. And that's it. Now we have an endpoint. So let's use it. First, we need to get an image to use. So I have a helper function here to process the image into a form that the model can use. This image may or may not be of my dog Yoshi. So let's see if we can use it for inference. Next, we create a SageMaker PyTorch predictor, giving it the name of the endpoint we created. Since the Torch Vision DenseNet model was saved with raw score outputs, we run the outputs through a softmax layer so we can get normalized probabilities. So that's what's going on here. Then we read the classes so that we can interpret the results. And then we print the top 5. And you can see that it does recognize that Yoshi is a dog. It seems to think my Shiba is a husky, but I'll give it a pass. That's pretty close. So we verified that the endpoint seems to work. It can do inference. Let's see how it's performing. Let's run 100 warm-up inferences to get it to steady state performance. Then the next thing we do is we run 1,000 more and keep track of the timestamps before and after so we can look up the CloudWatch metrics after the fact. And then we do just that. We have a helper function here. It uses the Boto3 library to fetch the CloudWatch metrics. And there's a model latency metric provided by SageMaker hosting automatically that we can just look up. So then we summarize the results below. You can see that we got 1,000 data points, just as we expected, and that the latency is about 45 to 50 milliseconds. So I copied this notebook with very minor modifications to use a CPU instance instead with no EI, so with no accelerator attached. And we actually upsized the instance type since we didn't have an accelerator to an ml.c5.xlarge. So let's look at the results there. Let's just look at the end here. You can see that we measure latency the same way and get much higher values, around 115 to 125 milliseconds. So you can see that even with better CPU instance, because you can see that the accelerator was doing the heavy lifting. Let's take a closer look at some performance numbers. We ran that same DenseNet 121 model on a few different CPU and GPU instance types, both with and without EI. And the results are summarized in these two graphs here. Note that in each graph, the two bars on the left are using EI, and the two bars in the middle are CPU instances, and the two on the right are GPU. So first, let's look at the latency graph on the left. You can see that the CPU instances have the highest latency, while the much more expensive GPU instances have the lowest inference latency. The latency when using EI offers an attractive middle ground that allows you to get your latency targets met, while also lowering cost relative to running the expensive GPU instances. To see that it lowers your cost, look at the cost per hour graph on the right. You can see that the per hour cost for EI is 93% lower than a P3.2x large GPU instance, which is the rightmost bar, and 61% lower than a G4DN.x large instance, which is the one next to that. I'll also point out that when using EI, because we're offloading the inference workload to the attached EI accelerator, we were able to use a less expensive CPU instance type than when we were only using CPU instances, without sacrificing any performance. In fact, the performance is much better than with the CPU instance alone. And the price per hour of the combination with the EI is actually very close to that of the standalone CPU instance used in the test. If you're running just a few instances 24/7 to handle your application's inference, then it'll probably work best if you choose the option with the lowest cost per hour that meets your latency requirements. Depending on your application's traffic patterns, it may be best to combine the two metrics shown here into a cost per inference metric for comparing the different options. So we ran those numbers for this model as well, and EI gave the lowest cost per inference of all the options shown. Next, we'll do another demo, second part, that shows using Elastic Inference for PyTorch models on EC2 instances directly. Elastic Inference uses VPC endpoints to privately connect the instance in your VPC with the associated Elastic Inference Accelerator that you attach to it. So before you can get started, you need to create a VPC endpoint for Elastic Inference before you can launch instances with accelerators. This needs to be done just one time per VPC. But without the setup, your instances can't connect to Elastic Inference. So it's important. You first have to set up some security groups. You can check the documentation for details. I have a link to the documentation in a later slide, but you can just look up the Elastic Inference Developer Guide to find it as well. There's also a helper script linked in the documentation to automate some of this setup for you, but I wanted to show you how it works with details so it's clear what's happening. So we create a VPC endpoint by going to the VPC dashboard and clicking endpoints on the left sidebar here, and then click create endpoint. Choose AWS services and filter Elastic Inference. You can see it right here. So you click that, and then you click all the supported AZs. And the next thing is you select a security group. I'm going to stop there since we already have an endpoint, but you would just select a security group and then you give it a name. Here, I'll go ahead. Select a security group, and then you just move forward in the process. You give it a name, and that's all. So once you have an endpoint set up, next you need to configure permissions by creating an IAM instance role with a policy that allows you to connect to an Elastic Inference Accelerator. So to do that, you go to the Identity and Access Management dashboard, click on Policies, and create policy. Click JSON, and then if you're looking at the documentation, you can copy the policy into the JSON and save it, give it a name. Again, we'll just cancel from here since we already have one in this demo, but I wanted to show you where that is. Once you've created the policy, you need to create a role that uses that policy to use for your instances. So you go to Roles, Create Role, choose EC2, Next, and then you find the policy that you created. This is mine. Check it. Go to next tags. You don't have to give it any tags unless you want to. Then review, put in the name and a description, and then you can create it. Again, I'll go ahead and cancel for this demo since I already have one. Now we're ready to create an instance. Everything's set up. So you go to EC2, launch an instance, and we're going to look for deep learning. And I chose the Amazon Linux AMI here. Once you've selected that, for m5.large, this is the kind we're going to launch. Configure instance details. Next thing you do is you pick a subnet supported by Elastic Inference. Choose the role you created, and then choose Add an Elastic Inference Accelerator at the bottom. Then you can choose the type. We'll choose EIA2.medium, and the number of them you want to create. And then from there, you can add storage, go through the rest of the process, and you've told EC2 that you want an Elastic Inference Accelerator attached to your instance. So now that we've launched an instance with an accelerator attached, let's use it. Here we have a script that loads a ResNext model that was trained with weekly supervised learning using a large data set of social media images with hashtags. We're using Torch Hub to fetch it. We load it with pre-trained weights and toggle inference mode with eval. Next, we make sure to disable gradients since we're just running inference. And then we trace the model on an image. And in particular, it's a random image of the right shape. It's just a random tensor. So we trace that model, and then we call TorchJIT save to save it to a file. It's that easy. Now we have saved the TorchScript model. Now over here in the terminal, you can see I have the script that we just looked at. So let's run it. So it traces that model on the input, and you can see now we have a file right here, which is the TorchScript model, the serialized TorchScript model that we can then use for inference. So let's look at the code that uses it and actually runs the inference using EI. But before we do that, just to avoid waiting, I'll go ahead and run this. So just to save some time of waiting on the script to run, we'll go ahead and start it running while we go look at the code. So let's take a look at the script that runs inference, which is currently running in the background. First, we define a function to pre-process the image into an input tensor of the right shape. Then we use that function to read in this image. That is not my kitten, if you're wondering. Next, we use TorchJIT load to load the model that we serialized before. Now let's run an inference. First, we disable gradient calculations, so we don't need them for inference. Then we use this torch.jit.optimize execution block function, this optimize execution here. What this does is it tells TorchScript, or it tells PyTorch that we want this model to be optimized for use with the EI accelerator, identified by EIA0, that EIA0 here. So this is the ID of the accelerator that we want to use. And that's all there is to it. This is actually the only change to get it to use Elastic Inference. So we run the inference just by using the model right here inside this block. After running one inference on the kitten image, we run the output raw scores through a softmax to get probabilities, and then print the top 5 classes and their scores, which is what this code is doing. So since we ran one inference, the next thing that we do is we run 30 more inferences and print out the latency so we can measure the performance, see how it's performing. And that's all there is to it. You can see we have the optimized execution call here again, saying that we want to use EI, but that's it. That's all it takes. So let's check on the result. You can see it quickly settled to a steady state performance of about 65 to 70 milliseconds. You can see that here. Oh, and of course, it correctly noticed that the image was a cat. Let's compare that to the version that doesn't use EI. I have a copy of this script that does EI. So let's see how the latency compares. So as you can see, the C version takes much longer to run each inference, since the EI accelerator is doing the heavy lifting to run the inference calculation. So you can get much lower latency by attaching an EI accelerator and making sure to change your code to use that. The EI version of the script was removing that optimized execution, the part that mentions EI. That's it. Let's take a closer look at some performance numbers. We ran that same ResNext WSL model on a few different CPU and GPU instance types, both with and without EI. So the latency graph on the left shows that EI offers a middle ground that allows you to meet your latency requirements while also lowering cost relative to the GPU. Again, you can see the EI are the two bars on the left, the CPU instances are the two in the middle, and the GPU two on the right. Looking at the graph on the right, the per hour cost for EI is 93% lower than the P3 and 61% lower than the G4DN.X large. This is true for EC2 as well as SageMaker. When using EI, we were able to use a less expensive CPU instance type, an M5.large, than when only using CPU instances, while achieving much better inference performance. And with a very similar price per hour as the CPU instance used, actually, as you can see. Also note, again, depending on your application's traffic patterns, combining these two metrics shown into a cost per inference metric may be best for comparing the options. We also ran those numbers for this model, and EI gave the lowest cost per inference of all these options. In summary, you can use Amazon EI to lower your inference costs by up to 75% by attaching EI accelerators to any EC2 instance, ECS task, or to SageMaker to right size for your application needs. You need little to no code changes, as you've seen, to use EI, since the interface is similar to using a GPU in these frameworks. Our customers are currently using EI for computer vision, NLP, and OCR use cases, among others, including image analysis for security, ballistic identification, post analytics, capturing handwriting on paper, social media image recommendations, and other use cases. And now EI has PyTorch support. So try it on all your PyTorch models. And finally, the best way for you to experience it is to try it out. Do a proof of concept, see how easy it really is to use it. I've included a few links here to the documentation and to a blog post that talks about using it for PyTorch, using Elastic Inference. And with that, we'll open it up for Q&A.